I want to start with the prehistory of the problem, and I would like to consider an approach for studying non-self-adjoint operators. As you know, if we have a self-adjoint operator, then there are many results in the framework of this theory, and frankly speaking, they are all not deserves to be considered for its kind of well-known theory. But if we have a self-adjoint, non-self-adjoint operator, that situation, I may say, is bad. So in this report, the first our aim to clarify the results obtained by Litsky, devoted to the decomposition on the root vector system of the non-self-adjoint operator. So I should clarify, if we have a self-adjoint operator, is a well-known spectral theorem in this case, but the situation, as I said, is very, very bad if we have non-self-adjoint operator. In this regard, we need to consider a so-called Schatten-von Neumann class. We know this notion, it's a well-known notion, but a very interesting thing happens if we consider some kind of a Schatten-von Neumann class and involve a notion of convergence exponent. So let us come to the terms of the entire function theory and consider a sequence of complex numbers such that monotonically increasing sequence. And let us consider a series and we consider such a value of P that this series is convergent. So infimum P such that this series is convergent, we consider such P that this series is convergent, is called the exponent of convergence, or convergence exponent. So, but in this case, the situation can be such that this series is divergent, but it may happen that it can be convergent. Here we involve this notion to study non-self-adjoint operators. For I should cite here the Litsky results. The results of the letter haven't covered the case if we consider the value of the exponent of convergence, and in this case we have that the series is divergent. So let us consider these questions more properly and in accordance with the operator theory. It's a kind of prehistory. Here I would like to present some brief historical review. The main paper I refer this one, summability of series in terms of the principal vectors of non-self-adjoint operators. Unfortunately, I don't think that it is translated in English, but frankly speaking, I don't know whether it is or not. A couple of words about the relevance of the consideration. In this case, we can cover a plenty of interesting operators such that well-known fractional integral differential operators, such that Kiprianov operator, difference operator, fractional difference operator, and Riemann and Riesz potential operator, and the approach is based on mostly general approach connected with the semigroup theory. We can generally describe in terms of operator theory, and in terms of semigroup theory, a rather wide class of operators, fractional integral differential operators, and the significance of such an approach is stressed, but that we can unify the approach and can consider harmoniously in the framework of one theory, one whole theory, except of several approaches nowadays spread all over the world by various mathematicians considering fractional derivatives from day to day and giving new notions of fractional derivatives. So here I would like to cite one of my paper. The paper established interesting properties, basic, I may say, properties of non-self-adjoint operators of one class that allows us to continue the reasonings and continue the studying of non-self-adjoint operators in the framework of spectral theory. Here, I would like to refer the previously well-known works in the framework of spectral theory: Katznelson, Crane, Marcus, Shkalikov. I want to stress your attention to the latter work by Shkalikov, and would like to show the fact that most of the previous papers deal with the decomposition of the operator on a sum, where the senior term must be either a self-adjoint or normal operator. And to apply the latter paper results for a concrete operator, we must be able to represent it by a sum, where the senior term T must be either self-adjoint or normal. So you see, it's a major condition to have some kind of representation in a sum where the first term must be so good, I may say. It's rather good to be normal in the framework of operator theory. But if we don't have such a representation, then I can offer an alternative approach realized in my paper, Asymptotics of Eigenvalues for Differential Operators of Fractional Order. And it was the first, I may say, paper devoted to this idea, and they considered fractional differential operators. But afterwards, I generalized the idea to the abstract non-self-enjoined operators satisfying some kind of equalities, and I'll show them further. The following papers are worth noting, for they deal with non-self-enjoined operators, but the main disadvantage to my mind is that the sufficiently good condition is imposed. They require that the numerical range of the operator, particularly eigenvalues, belongs to a parabolic kind domain. So many operators with self-enjoined major term can be considered in the framework of this theory. So these papers cover the operators with the self-enjoined senior term. But as I said previously, my own idea to consider non-self-enjoined operators that cannot be represented in a sum where the senior term is a self-enjoined operator. The central challenge of the latter paper, as I said, is how to create a model representing a composition of fractional differential operators in terms of the semigroup theory. So I want to say a couple of words. The main idea is in the following: if we have some semigroup, then we can consider a generator of this semigroup. If this semigroup is rather good or satisfies rather good conditions, well, then we can consider a generator. Frankly, for instance, if it's a semigroup of contractions, but then we can consider fractional powers of the generator. And this approach is very interesting, for it is unified and leads us to the notion of fractional derivative due to the Balakrushnian formula. So if we implement this approach and prove some theorems, spectral theorems, in the framework of this approach, then we can cover a plenty of fractional well-known derivatives. But the question how to consider a notion of fractional derivative deserves to be considered itself, for using the mentioned approach, I must say, I mean the approach I offered, we can query whether the new notion of derivative is satisfies generally to conditions to be called as a derivative or not. So we can't, in my opinion, we can't call by fractional derivative everything whenever we want. So here I cited my teacher Nakhushev. He one of the first considered the eigenvalue problem of the operator of the second order with the fractional derivative in lower terms. I want to show the main my approach, and here I choose the notion of the operator order. You see below, if you don't know this notion, I can show it to you if you ask me. So in accordance with this approach, we can use a very relevant results, for instance, described in the monograph of Rosenblum, and we can use these results to study the properties of non-self-enjoined operators. In what way, we will see further. Basic literature that can interest you, I present here. So let us consider the way of approach. Considering an arbitrary compact operator B acting in a Hilbert space such that a numerical range of the operator B belongs to the sector with the text situated at the zero and the semi-angle. So here we have a sector, and we have and the numerical range of the operator So numerical range is numbers, frankly speaking. Here we have f from the domain of definition of the operator B, but here we consider numbers, and the additional condition on f So here we consider these conditions, and it implies, this condition implies that numerical range belongs, the values of this quadratic form belongs to the sector, you see. But here we have a rather wide conditions imposed upon the semi-angle. And this, in my opinion, main advantage of the Litsky results, not only consider non-self-enjoined operators, but consider very, very wide conditions imposed upon the sector. So we can consider a contour on the complex plane. We need this notion, and afterwards we will consider some formulas using this notion. And what should we do with the non-self-enjoined operator? Certainly, if we refuse such great and strong property as self-adjointness, we should require some other conditions. I did it. The hypothesis H1 and H2. We impose conditions on the quadratic form of the operator, on the ciscollinear form of the operator, more precisely. We will use these notations and consider order of the operator. Firstly, we consider general statements, prove the made refinement related to the involved notion of the convergence exponent, as well as newly constructed sequence of contours, allowing us to arrange the eigenvectors in the power type way. We used this expression following the literary style of the monograph by Litsky. We implement the approach that refers us to the notion operator order. It gives us an opportunity to reformulate results of the spectral theory in the more convenient and applicable way. The theorems given below gives us tool to study the existence and uniqueness theorems in the abstract Hilbert space. Moreover, we obtain a solution that can be represented by the series on the operator A root vectors with the coefficients where the index relates to the eigenvalue, the index C relates to the geometrical multiplicity, the index I relates to the algebraic multiplicity. The convergence is understood in the Abelitsky sense. The following relation is a central aim of the Abelitsky concept of decomposition on the root vector series. So I would like to draw your attention to this formula, formula 1. Here we have a representation of the integral in the series, and this gives us many opportunities. And so let us study the cases when we can obtain this representation. We can choose a contour in various ways. It depends on the conditions imposed on the operator, but we would like to denote it by this term, by this letter. So right now I would like to define a Schatten-von Neumann class of the convergence exponent. Here we consider Schatten-von Neumann class. You see, it denotes the Schatten-von Neumann class. But here we consider additional relation that this relation holds for arbitrary small positive epsilon. Recall that in the paper by Litsky, there was constructed a sequence of contours of the exponential type. The condition is imposed. So here I should recall to you that alpha is defined in the formula 1, you see? And what about a sequence of contours? It's a central point of this theory for the question how to summarize this series is rather difficult and interesting. We can do it only choosing sequence of contours. You see, here we have some kind of lacans here, and only just in this way we can summarize this series. Certainly, convergence is understood in the sense of norm in the Hilbert space. So the case when alpha equals to the convergence exponent didn't consider by Litsky, and I tried to make some refinement to his interesting results, and in this way I came to the interesting result itself. I discovered that in this case the sequence of contours can be chosen is in I may say not exponential way but power type way. So here we see that conditions H1, H2, right now I want to recall to you what is it, H1, H2 conditions gives us an opportunity to claim that this relation holds, you see, and it implies generally that we have range for the semi-angle, you see. But frankly speaking, to obtain results using the scheme discarded by Litsky, for us it's not good range for semi-angle, and this is why we should involve additional condition. Frankly speaking, this condition, I think in some cases can be treated as belonging of the numerical range of the operator to a parabolic type of domain, and it intersects with the results of Agranovich and Marcus mentioned by me previously. But we can consider this condition separately, additional condition, and at any rate, the results are relevant if we consider only H1, H2, but additionally H3 gives us more opportunities. So in this case, we consider another contour. Previously we defined contour of integration, but here we consider this kind of contour. Main results. The theorems given below devoted to the proof of the relation 1. You see, I should recall relation 1, this decomposition on the series. They are formulated under the assumption that either the condition holds or the condition IH3 holds. I mean, additionally, in both cases, we think that conditions H1, H2 hold in both cases, but additionally, we should impose these conditions. And respectively, we should denote by this letter a contour of integration, and in this case we can formulate theorems in the unified form. So we have the improved theorem 1. Assume that the numerical range belongs to the sector with the text situated at the point 0, the condition on the semi-angle, and resolvent. Here we denote by this letter resolvent of the operator W. You see, it's a shortage. Belongs to the Schatten-von Neumann class of the convergence exponent. Conditions on rho, and the interesting case appears if A belongs just this class. So we can't say that this a pure Schatten-von Neumann class. You see, But in this case, we need additional condition, this condition. So in this case, a sequence of natural numbers can be chosen so that relation 1 holds. So we can choose such a sequence that relation 1 holds. But frankly speaking, somebody would like to ask me, maybe we shouldn't choose any kind of way to consider a sequence of numbers, and this series can be convergent in any case. Frankly speaking, the Litsky demonstrated example that it is not. It is not, and here we can regulate the convergence only by choosing a corresponding sequence of numbers. So this kind of generalization, this theorem 1, devoted to considering the convergence exponent. But theorem 2 more interesting, for in this case we can choose, I said, a power type sequence for the eigenvalues corresponding to the counter can be their difference can be estimated in this way. Their difference can be estimated, and we see as Litsky said that eigenvalues are close in the exponential type, but here we see that they are close in some kind of power type. You see, so here I should demonstrate it using the series. You see, here we have root vectors, root vectors corresponding to the eigenvalues, and they are all here. This lacan is here. You see, this number and this number, and we can consider them here. You see, the difference between the eigenvalues in the framework of one sum in the series less than this value. Theorem 3 is very interesting, for it covers the so-called case of the convergence exponent, and here we impose some kind of logarithmic equality except of instead of the equality corresponding to the operator order, and here we can claim that relation 1 holds, and the sequence of the eigenvalues can be chosen, a sequence, sorry, of natural numbers can be chosen so that this relation holds, and the series 1 is convergent in the way mentioned above. I want to show some kind of picture, maybe some questions beforehand. So if you don't, I want to show one picture to you. Excuse me for demonstrating Russian literature. I address this expression to English-speaking people, but I don't want to show Russian text. I only want to show one picture, and in this case, the language doesn't matter, I suppose. So you see, Litsky considered exponential type of sequence. You see, here we have estimate, and here we have exponent. You see, and the main idea is in the following, that we consider two eigenvalues. We can choose two eigenvalues, and between them there are not eigenvalues. It's a kind of lacan. You see, it's a natural lacan. Natural, why? For we don't want to apply any force to create it. In the contrary to the case, to the so-called case of non-natural lacan, where we can create a lacan but not naturally with some technique. This approach was properly studied by Marcus. It's a very interesting approach, and afterwards was considered by Agaronovich and implemented to some operators with the parabolic kind domain containing the numerical range. So here we have a lacan, but here a group of eigenvalues is situated between the eigenvalues, and mind you that the very group of eigenvalues lie in the series I represented in the slide. You see, right now I want to be back to the slide and show it to you one more time. You see, this group of eigenvalues, here we have root vectors corresponding to them. You see, is presented here, and convergence is has this kind of nature. So I think my report is a little bit philosophical, but frankly speaking, we have a huge amount of the information, and it can't be presented so shortly and quickly. I tried to reveal, and I try to convey my imagination to you, but you can find this information in the papers presented in archive site and so on. What about applications? Firstly, we can consider evolution equations in the abstract Hilbert space, and the application is rather relevant. And I want to demonstrate one concrete case that we can study using simple technique. I think everybody can understand this in short time, I mean. So let us consider a Cauchy problem of this kind, abstract Cauchy problem, where the operator W is satisfied the hypothesis H1, H2. So we have a theorem. Assume that conditions of one of the theorems 1, 3 hold. I recall that they establish the convergence of the series mentioned by me, under the assumption that alpha is alpha equals to n. You see, we have a strict equality. Then there exists a solution of the Cauchy problem in the form 1. A sequence of natural numbers can be chosen in accordance with the claim of the corresponding theorem. Moreover, the existing solution is unique if the operator is accretive. So I think I should show to you what is it in the form 1. In the form 1, in this way. So we can represent a solution of the equation in this way, in this form. I may say in exact form, if we know the root vectors, the coefficient C can be calculated if we know the root vectors. And as the application, and to stress the difference between the results of mine and results by Litsky, I would like to consider artificially constructed normal operator, for which just results of mine can be applied, and it can't be covered by results of Litsky. Firstly, I would like to present an example. Consider such a sequence. You see mu with the index n sequence. So this relation on Q, we can show easily then this relation holds. You see, we can calculate easily this. What gives us the fulfillment of the first condition? First condition here is it is. At the same time, this condition is one second. I think I lost one expression. Sorry. I would like to show that this condition, this sequence satisfies. If we consider this sequence, then this series is divergent. But at the same time, this condition holds at the same time. So we are interested in just in very sequence, for it indicates the difference between results. Right now, consider the abstract separable Hilbert space H and an operator N acting in the space as follows. So we constructed it having a sequence of eigenvalues. We constructed it. So if we have a separable Hilbert space, then we have an orthonormal basis, and sequence mu n is defined in the considered above example 1. But sequence eta is satisfied the following condition. We construct it artificially, imposing this condition. Define the space H plus as follows. You see, it's space H plus. And it's clear that H plus is dense in H, since the basis belongs to H plus, and it's a basis of our separable Hilbert space. Let's show that embedding of the spaces is compact. For this purpose, consider the operator B defined as follows. And the fact that B is compact operator can be proved easily due to the well-known criterion of compactness in the Banach space endowed with a basis. This theorem can be found, I think, in regular literature, functional analysis literature. For instance, Lusternik-Sobolev. If you want to find this theorem, you can choose Lusternik-Sobolev. Notice that if F belongs to H plus, then G belongs to H. it's a simple thing and can be calculated directly, where G is defined by its Fourier coefficients. By virtue of such a correspondence, we can consider any bounded set in the space H plus as a bounded set in the space H. Applying the operator B to the element G, we get the element F. Since B is a compact operator, then we conclude that the image of the bounded set in the sense of the norm H plus is a compact set. So since B is a compact operator, then it maps any bounded set to a compact set. Let us define the set M as a linear manifold generated by the basis vectors. Thus, we have obtained the relation H plus and H. Here, this sign denotes a compact embedding and established the fulfillment of the condition H1. The first relation of the condition H2 can be obtained easily due to the application of the Cauchy-Schwarz inequality. To obtain the second one of the condition H2, I mean, we should note that we have, due to, I recall, due to this condition, you see, due to this parabolic kind condition, we obtain these relations. So we can claim that hypothesis H1, H2 hold. Moreover, we can show that condition H3 is satisfied. In this case, we should only estimate this relation and we can get easily this. So right now we have fulfillment of conditions H1, H3, and in this case we can consider as a right-hand side this power of the operator n, and can consider a Cauchy problem of the evolution equation. We can apply Theorem 4 and claim that there exists a solution of this equation. Moreover, we can show that this operator is accretive, and in this case, if it is accretive, I note we try to show it. It's not a hypothesis. We calculated right here. We can claim that the solution is unique, and we can represent the solution in the series 1. So I may say that is all. I'm waiting for your questions. Thank you very much.